Alright, so this is going to be a video about how to derive the electric field, a distance d from a finite wire. So if we go down here, we have our picture. So you can see I've drawn this wire and it has a length of L, and we have split it in the middle here, and we have a point here that is a distance d from the wire, and it's right in the middle. Don't forget that part. And so if we take a very small sliver dx of the wire, and we say it has a very small charge dq, and we say that it exerts a very small electric field dE, you can see where this is going. We're going to get to some calculus later. And that the charge density on this rod is lambda, which is in coulombs per meter, then we can say that the dq, the very small charge here, is equal to lambda times dx, which is the charge density times the very small part of the rod, where the very small part of the rod is a distance x away from the center of the rod. And we can see that over here we have the distance r. R is the distance from our little part of the rod dx to our point that we're interested in, and right down here we're going to define r as x squared plus d squared square root, and you can see that because it's a right triangle here, and we're going to save that for later. We're going to use it later. So if we go up here, we can see, so we can say that the electric field equation kq over r squared, where the first part is the magnitude and the r hat times the r hat is the direction, then we can say that our very small dE equals k times the very small q dq divided by r squared times r hat. And if we take our equation that we made before, where dq is equal to lambda dx, we get this next part of the equation, which is that k lambda dx over r squared times r hat. And then if we use our other equation that we defined as r being d squared plus x squared, where r is how far the specific part of the rod is away from our point that we're interested in, we can say that k times lambda times dx divided by d squared plus x squared, because we get rid of the square root because it's squared, times r hat, and that's the very small dE. However, we still have this r hat, which we can use to split up into components, the dE. So we can go down here and see that dE is equal to dEx is equal to the dE times cosine of theta, where we can see, well, I'll show you what cosine of theta is in a second. And what we've done here is we've plugged in dEx that we figured out before, k lambda dx over d squared plus x squared. And now we need to find out what that cosine theta is. So there it is, but let's go see this picture over here. So what we have here, so we can see that here's the dEx, and we can see here's the theta, here's the same theta, and we can look at this triangle, and since it's a right triangle, we can say that the cosine of theta is actually x over the square root of x squared plus d squared. That's what we can say for cosine of theta right here. However, now you have to look at a picture to see this next part, is because we have this rod, if you remember, and it's a length L, but we've split it in half. So because it's symmetrical, and because the charge density is all the same, and it's a symmetrical rod, each section of the rod over here is going to match a section of the rod over here, and they will contribute equal and opposite forces in the electric field in the x direction, and therefore due to symmetry the actual dEx is 0 in this case. So now we'll go on to DEY. And DEY is equal to DE sine theta. Here we go, I've plugged it in here. The DE that we found before is right here in orange. And over here, we've gone back to the triangle, and we've defined sine of theta as d over x, the square root of x squared plus d squared, because sine of theta is opposite over hypotenuse of the triangle. And that's how we got that sine theta. And now if you combine these, multiply these together, because we're going to get DEY equals dk lambda dx divided by x squared plus d squared to the 3/2 power. Now we get to the calculus. So in calculus, we know that the full electric field EY is going to be equal to the integral of DEY. So we plug that in down here. Therefore, we have the electric field is equal to the integral from negative L over 2 to L over 2, which remember is the full entirety length of the rod. And we integrate dk lambda dx divided by x squared plus d squared to the 3/2 power. Now I'm not going to do any calculus here because it gets rather confusing, and it's actually a complicated like substitution and some complicated calculus. So really, usually you can just look up something for this, where in the back of a physics textbook it'll have a little substitution thing, and you can look up the 3/2 power. So use a formula, and you can get that the electric field equals k lambda L, where L is the length of the rod, divided by d times the square root of d squared plus L over 2 squared. And there you go.